This video was sponsored by CuriosityStream. Earthquakes are the most fatal natural disasters. According to a report from the United Nations Office for Disaster Risk Reduction, in the period from 1998 to 2017, earthquakes accounted for 7.8% of natural disasters, but for 56% of deaths from natural disasters. Why is it so hard to predict earthquakes? Did you know that the number of earthquakes correlates with solar activity and with the length of the day? You didn't? Well, then stay tuned, because that's what we'll talk about today. This is the first part of a two-part video about earthquake prediction. In this part, we'll talk about the long-term and intermediate-term forecast for earthquake probability, ranging from centuries to months. And in the second part, which is scheduled for next week, we'll talk about the short-term forecast from months to seconds. First things first, why do earthquakes happen? Well, there are many different types of earthquakes, but the vast majority of large earthquakes happen in the same regions over and over again. You can see this right away from this map, which shows the locations of earthquakes from 1900 to 2017. This happens because the surface of Earth is fractured into about a dozen pieces, the tectonic plates, and these plates move at speeds of a few centimeters per year. But they don't all move in the same direction, so where they meet, they rub on each other. Those places are called faults. Most of the time, a fault is locked, which means that resistance from friction prevents the rocks from moving against each other. But the strain in the rock accumulates until it reaches a critical value where it overcomes the frictional resistance. Then the rocks on both sides of the fault suddenly slip against each other. This suddenly releases the stress and causes the Earth to shake. But that's not the end of the story, because the plates continue to move, so the strain will build up again and eventually cause another earthquake. If the motion of the tectonic plates was perfectly steady and the friction was perfectly constant, you'd expect the earthquakes to happen periodically. But reality is more difficult than that. The surface of the rocks isn't exactly the same everywhere, the motion of the plates may not be entirely steady, the earthquakes themselves may change the rocks, and also earthquakes in one location can trigger earthquakes elsewhere. This is why earthquakes recur in irregular intervals. In a nutshell, it's fairly easy to predict where big earthquakes are likely to happen, but difficult to predict when they will happen. According to the website of the US Geological Service, neither the USGS nor any other scientists have ever predicted a major earthquake. We do not know how, and we do not expect to know how any time in the foreseeable future. Okay, so that's it. Thanks for watching. No, wait. That's not it, because even though no one knows how to predict an individual earthquake, we still might be able to predict the probability that an earthquake occurs in some period of time. This sounds somewhat lame, I know, but this information is super important if you want to decide whether it's worth investing into improving the safety of buildings or warning systems. It can save lives. And indeed, geophysicists know some general probabilistic facts about the occurrence of earthquakes. The best known one is probably the Gutenberg-Richter law. The Gutenberg-Richter law is a relationship between the magnitude and total number of earthquakes which have at least that magnitude. Loosely speaking, it says that the number of large earthquakes drops exponentially with the magnitude. For example, in seismically active regions, there will typically be about 10 times more events of magnitude 3.0 and up than there are of magnitude 4.0 and up, and 100 times more earthquakes of magnitude 2.0 and up than of magnitude 4.0 and up. You get the idea. The exact scaling depends on the region. It can actually be larger than a factor 10 per order of magnitude. The US Geological Service has in the past used records of seismic activity in the San Francisco Bay Area to predict that the area has a 75% probability of an earthquake of at least magnitude 6.0 before the year 2043. Geophysicists also know empirically that the distribution of earthquakes over time strongly departs from a Poisson distribution, which means it doesn't look like it's entirely random. Instead, the observed distribution indicates the presence of correlations. They found, for example, that earthquakes are more likely to repeat in intervals of 32 years than in other intervals. This was first reported in 2008, but has later also been found by some other researchers. Here is, for example, a figure from a 2017 paper by Bendick and Bilham, which shows the deviations in the earthquake clustering from being random. So a completely random distribution would all be at zero, and the blue curve shows there's a periodicity in the intervals. That there are patterns in the earthquake occurrences is very intriguing, and the reason why geophysicists have looked for systematic influences on the observed rate of earthquakes. We have chosen here 3 examples that we totally subjectively found to be the most interesting: solar activity, tides, and the length of the day. I have to warn you that this is all quite recent research and somewhat controversial, but not as crazy as you might think. First, solar activity. In 2020, a group of Italian researchers published a paper in which they report having found a very strong correlation between earthquakes and solar activity. They analyzed 20 years of data from the SOHO satellite about the density and velocity of protons in the magnetosphere, so that's about 500 kilometers above the surface of Earth. Those protons come from solar wind, so they depend on the solar activity. And then they compared that to the worldwide seismic activity in the corresponding period. They found that the proton density strongly correlates with the occurrence of large earthquakes of magnitude 5.6 and up, with a time shift of 1 day. The authors claim that the probability that the correlation is just coincidence is smaller than 10 to the minus 5, and the correlation increases with the magnitude of the earthquakes. The authors of the paper also propose a mechanism that could explain the correlation, at least qualitatively, namely a reverse piezoelectric effect. The piezoelectric effect is when a mechanical stress produces an electric field. The reverse piezoelectric effect is, well, the reverse. Discharges of current from the ionosphere could produce stress in the ground. That could then trigger earthquakes in regions where the stress load was already close to rupture. A few other groups have since looked at this idea, and so far no one has found a major problem with the analysis. Problem with using solar activity to predict earthquakes is, well, it's difficult to predict solar activity. Though the Sun is known to have a periodic cycle, so if this result holds up, it'd tell us that during years of high solar activity, we're more likely to see big earthquakes. Second, tides. The idea that tides trigger earthquakes has a long history. It's been discussed in the scientific literature already in the 19th century. But for a long time, scientists found statistically significant correlations only limited to special regions or circumstances. However, in 2016, a team of Japanese researchers published a paper in Nature in which they claimed to have found that very large earthquakes above magnitude 8.2 tend to occur near the time of maximum tidal stress amplitude. They claim that this result makes some sense if one knows that very large earthquakes often happen in subduction zones, so that's places where one tectonic plate goes under another. And those places are known to be very sensitive to extra stress, which can be caused by the tides. Basically, the idea is that tides may trigger an earthquake that was nearly about to happen. However, it isn't always the case that large earthquakes happen when the tide is high, and also there are very few earthquakes of that high magnitude overall, which means the correlation has a low statistical significance. Third, the length of the day. As you certainly know, the length of the day depends on which way the wind blows. Okay, in all fairness, I didn't know this, but if you think about it for a second, this has to be the case. If the Earth was a perfectly rigid ball, then it would rotate around its axis steadily because angular momentum is conserved. But the Earth isn't a rigid ball. Most importantly, it's surrounded by an atmosphere, and that atmosphere can move differently than the solid sphere. This means if the wind blows in the other direction than the Earth is spinning, then the spinning of the Earth has to speed up to preserve angular momentum. In physics, this is a small effect, but it's totally measurable and on the order of some milliseconds a day. Indeed, you can use the length of the day to draw conclusions about annual weather phenomena, such as El Niño. This was first shown in a remarkable 1991 paper by Hyde and Dickey. Have a look at this figure from their paper. The horizontal axis is years and the upper curve is variations in the length of the day. The lower curve is a measure for the strength of the southern oscillation. That's a wind pattern which you may know as the El Niño-El Niño years. You can see right away that they're correlated. Yes, so the length of the day depends on which way the wind is blowing. The fluid core of the Earth is also sloshing around and affects the length of the day, but this effect is even smaller than that of the atmosphere and less well understood. Fun fact, the fluid core is only about 3,000 kilometers underneath your feet. That's less than the distance from LA to New York. But back to the earthquakes. Earthquakes make the Earth more compact, which decreases the moment of inertia. But again, angular momentum is conserved, so earthquakes shorten the length of the day. But that's not all. Geophysicists have known since the 1970s that seismic activity correlates with the rotation of the Earth and therefore with the length of the day, in that shorter days are followed by more earthquakes with a time lag of about 5 years. Since the 1970s, data have much improved and this finding has become somewhat more robust. Based on this, Bendick and Bilham made a forecast in 2017 that in 2018 we would see an uptick in earthquakes. The number of large earthquakes since 2018 is within the uncertainties of their forecast. Yes, correlation doesn't necessarily imply causation, but correlations are useful for forecasting even if you don't understand the causation. Just why that happens is presently rather unclear. Bendick and Bilham suggest that earthquakes are weakly coupled by the rotation of the Earth, and when that rotation frequency changes, that may cause a cascade effect by inertia, basically. You can imagine this as follows. The Earth spins and all those plates on it spin with it, but when the spinning changes, it takes some time until the plates get the message. And then they don't all react the same way, which may cause some extra stress. That triggers earthquakes in some places, and those trigger further earthquakes. So it's not like the changes in the rotation actually cause earthquakes. It's just that they advance some earthquakes and then retard others because the stress between the plates was released early. But really, no one knows whether this is actually what happens. As you can see, geophysicists are teasing out some really intriguing systematic correlations that may lead to better long-term predictions for earthquake risk. And next week, we'll talk about short-term predictions, among other things about whether animals can sense earthquakes and whether earthquake lights are real. This video was sponsored by CuriosityStream. One of the cool things about having a YouTube channel is that I get to try out what other platforms have to offer for science education and entertainment, so I can tell you about them. And this week, we have a new sponsor, CuriosityStream, which you've probably heard about. CuriosityStream offers thousands of movies and shows about physics, space, medicine, technology, history, everything really. And you can watch them conveniently on your laptop or phone. If you always thought geology is kind of boring, I recommend, for example, their documentary A Day in the Life of Earth about what's going on under our feet and how the forces of nature change our planet, both slowly, like erosion or the movement of tectonic plates, or rapidly, like volcano eruptions. And of course, I have a special offer so you can try it out yourself. You can get a subscription for CuriosityStream for an entire year for just $14.99 if you use our link curiositystream.com/Sabine or use the code Sabine at checkout. So have a look at this, but don't forget to come back next week.